Hi, my name is James Jones, and this is my Lab 1 on constant velocity for physics. So, in this lab, we aim to investigate the motion of an object moving at a constant velocity and compare the real motion of that object to the ideal motion of an object moving with constant velocity as predicted by a computational model using Newton's second law. So, why would we want to do this? Well, we're trying to determine whether an object moving in real life at a constant velocity would actually follow the path predicted by Newton's second law of an object with zero net force acting on it. And for this lab, I decided to observe the motion of a ping pong ball as it moves to the left along a flat surface. So, what is Newton's second law? Now for this lab, we're using the form of Newton's second law that states the final velocity is equal to the initial velocity times the net force divided by mass times the change in time. The net force divided by mass is the acceleration of an object. Because we want to maintain a constant velocity, V final must be equal to V initial, which means that there's no acceleration, which means that the net force must be equal to 0 in this system. And if the net force is 0, we can also calculate the final position by using this equation down here, which says the final position is equal to the initial position plus this constant velocity times the change in time. These are the principles that our computational model will be based on. So, to track the motion, we used a program called Tracker, which tracks the motion of the ball in each frame and will automatically generate a plot summarizing the data. As you can see, we use the tracker point in each frame, and then it gives us the changes in position and the changes in time. So, we're going to compare this data we got from Tracker to the computational model that's on the next slide. So, for the computational model, I used a program called GlowScript to simulate an object with the same starting conditions as my ping pong ball in Tracker, moving at a constant velocity. As you can see, we have the mass of a standard ping pong ball input here, and we also have the initial position and the initial velocity, which we got from Tracker by taking the change in position from the first two frames divided by the change in time. And then we use that as our initial velocity in this system. So, how did we incorporate Newton's second law into the model? Well, as you can see, we have the net force as 0 here, and then we have the ball's velocity, defined as the final velocity equals the initial velocity, plus the net force divided by the mass times the change in time. As you can see, this is the exact same equation as we defined earlier as being Newton's second law. We also have the same position equation saying that the final position is equal to the initial position plus the change in the velocity times delta t, which should remain constant because we have a constant velocity. So, here's the results that we got from our model. As you can see, our experimental data follows the model data almost exactly until it starts to deviate towards the end as the model becomes an overprediction and the actual ping pong ball seems to slow down. So, why does this happen? Well, as we can see in the graph, the ping pong ball slows down at the end, and this is because our predicted model is based on an ideal environment where the net force is 0 and the object travels at a constant velocity. But in the real world, this is not actually the case. The net force on the ping pong ball is not 0 because it encounters friction from the table and air resistance as it rolls. These cause the ball to lose momentum as it travels, which in turn means the ball is losing velocity as time goes on. This is shown in the graph where the experimental data slope gradually decreases, which means that the ball is losing velocity because the slope of the position versus time graph is velocity. So, any other deviations in the graph could also be explained due to human error in placing the tracking points, and that in the video, the ball also travels slightly backwards in addition to just moving to the left, and this would also make the position points at the end of the video closer together. So, what does this mean? Well, our results show that the motion of an object in real life traveling at a constant velocity relatively matched the ideal motion of an object traveling with a 0 net force according to Newton's second law. Even though there was some deviation in the graphs, this is mostly due to non-ideal conditions such as the friction of the table and human error in the tracking points. So all that we can really draw from this is that when an object travels at a constant velocity, the net force on the object is 0. We can't actually conclude anything about the individual forces on the object or how many forces there are using Newton's second law. So, how could this be improved? This experiment could be improved by observing an object moving in an environment where the net force is as close to 0 as possible with no friction or air resistance affecting the object. While we may not be able to do this ourselves, this could be done in using a vacuum in outer space. In this environment, the ball would encounter negligible friction and air resistance and should travel in a manner more similar to what we found in our model. This could also be improved by using a method to track the motion that tracks the exact same spot in the ping pong ball as it moves, which would take away the human error from Tracker. And I'd also just like to take a moment to talk about our axes in this problem. So the way that we had our axes set up means that the ball is moving in the negative direction. But if we had flipped them so the ball would be moving in the positive direction on our axis, This wouldn't really change the relative motion of the objects in comparing the two data points, but it would mean that they would move in the positive direction instead of the negative direction, which is what we see here. So that would conclude my lab. I thank you for your time. Have a good day.